So the last part we're going to discuss is just like how we have expected value and standard deviation, we have the same thing with binomial random variable. So it's pretty similar, and then we'll discuss the distribution itself and what that looks like. So here, if we look at the mean and standard deviation of a binomial random variable, we can see they're pretty simple formulas, which are on your formula sheet. So you would just plug and chug them into the calculator. And remember that the mean tells us the long run. So in the long run, we can expect what from our households owning 3 or more cars, right? And then the average distance, the give or take part. So according to that same study, right, we have a sample of 400 owning cars households. Let's determine the mean and standard deviation. So now our trials have increased, right? So the first thing we want to note would be the fixed number of trials is now 400, and our probability of success is still 0.35. So if I find the mean with respect to this random variable, that would just be 400 times 0.35, which is equal to 140. And then if I wanted to find the standard deviation with respect to the household, that would just be the square root of 400 times 0.35 times 1 minus 0.35. So you would just follow the formulas right up here. And if I put that in my calculator, I get something like 9.5. Okay, so those are the numerical values, but what does this mean in terms of the actual car owning households, right? So we could just say that in the long run, we can expect 140 households to own 3 or more cars, give or take 9.5 households. So we do have numerical values that we can use, but you know, interpreting this in context of the problem, we still look at it as a long run effect. Okay, so super simple, right? All right, so now let's just talk about the distribution itself. Binomial probability distribution is very dependent on the number of trials and success. And so we just want to look at the left column and the right column. Let's see if I can scroll down a little bit. There we go. So notice on the left column, our number of trials stay the same. Okay, and I'm just going to draw a little line here. And notice the probability of success increases. So when the probability is at 0.2, notice it's skewed right and it tails off to the right. Notice when the probability is 0.5, which is a half or 50%, notice it kind of gives this nice little bell curve, right? And when the probability is close to 1.9, it actually ends up being skewed left. So there's something special about the probability of success being 0.5. And what it is when the probability is less than 0.5, we get some skewness. In fact, we get skewed right. When we get a probability that is 50% or a half, it's normal, or we call it a bell curve. Symmetric, I think we have also called it. Another one is if the probability of success is larger than a half, it moves and it has some skewness and it's skewed left. So the effective probability of success is really what we want, is the probability that's not really around 50% that gives us the bell curve. But that's just not the way the world works. So at least when we know the probability of success, like let's just say for the cars, that was less than a half, right? That was 0.35. So we know our probability distribution for a certain number of trials will be skewed right no matter what. Okay, now let's look at the right column and look at the probability of success and the trials. Okay. We can see that the probability of success is the same for each one, but the number of trials, oh, that did not turn out nice, all right. Here we go. There we go. The number of trials is increasing. So what happens when we fix the probability of success and increase the number of trials? And this is similar to what we just did, right? We had 20 households the whole time, and then we increased it to 400. So this is kind of our situation of why did we do that and how is that affected? So notice when the probability is the same, but you have a small number of trials, we get some skewness, right? And as it increased, like I doubled the trials here, right, from 4 to 8, it kind of, the peak moved a little to the right, right? This little thing moved a little to the right. And if I totally jump and increase it completely like this, so the larger number of trials, notice it becomes more bell curve. So what does this mean? This means that despite the probability of success, as n gets larger, the distribution becomes more bell-shaped or bell curve. And this is really from the law of large numbers, right? I kept saying, like, as long as we take enough trials, how many is enough? Well, enough, right? Enough where we can actually see a reflection of the true population. As the number of trials gets larger, as you toss that coin a million times, a gazillion times, a gazillion times, the more and more you take those trials, the more and more you get to the true probability. And in this case, the more and more the bell curve, the probability distribution for binomial experiments become more bell curve. This isn't just a coincidence. It's the law of large numbers. So the role of n in a binomial distribution means that as the number of trials n increase, the probability distribution of the random variable becomes bell-shaped. And a general rule of thumb to make sure this happens is this calculation here, this inequality. So let's just take, for example, the previous example when I had 400 cars and the probability of success was still 0.35 and the probability of failure was 0.65. Let's see if this is actually true, because this happened to us, right? We went from 20 to 400, and so we should have got a bell curve despite our probability of success. Meaning that if I do this product, this left side of the inequality will be larger than or equal to 10. So let's try that. So we have 400 times 0.35 times 0.65. And I will see if it is larger than or equal to 10. I assume it is. we get 91, which is greater than or equal to 10. So we're going to be using this more and more in the future. So get used to kind of keep this in the back of your head. It's also on the formula sheet, so you don't have to memorize it, but you definitely should know when to use it.